All right, given hydrocyanic acid, HCN has a Ka value of 6.2 times 10 to the negative 10. We are first going to write the ionization equation or dissociation equation for hydrocyanic acid. So this means I want to place aqueous hydrocyanic acid in water, and I want to show how it's behaving as an acid. So by definition, an acid is a proton donor, meaning it essentially is donating a hydrogen positive 1 ion. So that hydrogen breaks off of that acid and it joins the oxygen of water, creating the hydronium polyatomic ion, the +1 charge, and leaving behind the cyanide polyatomic ion with a -1 charge. Okay. A couple things to note here. I am using a double arrow to signify that this is a reversible reaction. And I know that this is going to be heavily reactant favored because take a look at that Ka value. That's a really small, very, very, very small Ka value, meaning that this is heavily reactant favored, which really means you're going to have a lot more of the whole hydrocyanic acid at equilibrium. You're going to have lots of reactant at equilibrium and very little of your products, which tells me that this is a weak acid because not so much of this acid is producing the product ions. So that's just one context clue that I can use here to say that hydrocyanic acid is definitely a weak acid because look at that Ka value, 10 to the -10. And I know that hydrocyanic acid is not one of my 6 strong acids that I have memorized. So part 2 here, write the Ka expression for hydrocyanic acid. So just like any other equilibrium constant, K is equal to products over reactants, and coefficients are used as exponents. We know that we use square brackets to indicate concentration, and we know that we're not going to include liquid water because we never include liquids or solids in K expressions. Part 3. Let's say we have a 3 molar hydrocyanic acid solution and we want to calculate the pH. Well, we know that pH is equal to the negative log of concentration of H, or in other words, the negative log of hydronium. Remember that hydronium and hydrogen are used interchangeably in all these problems because hydronium is just water plus that hydrogen ion, and we know all of our solutions are occurring in aqueous solution where water is our solvent, so we use them interchangeably. They mean the same thing. So essentially I need to know how much hydrogen or hydronium is present at equilibrium for this acid. So this involves writing out that balance equation again and creating an ice chart. Okay, so our initial concentration of acid is 3 molar for this problem. When I get to water, no one cares about water because it's a liquid. Yes, we know it's there, but because it's a liquid, we really ignore it. Both products will start off with molarities of 0. So right away I see, hey, I've got zeros on my product side for my initial. I know that anytime I have a 0, we're moving towards the side with a 0. So for our change row, that means we're going to move to the right. We're moving towards that product side. So minus X from our reactant plus X and plus X for our products. So at equilibrium, our acid is 3 minus X, and both of our products are X. Keep in mind, what we're trying to do is calculate the pH, which is the negative log of H. And it's the H at equilibrium. So what are we really taking the negative log of? We're really taking the negative log of x from our ice chart. So we somehow had to solve for x. Well, you already wrote the Ka expression. You were given the Ka value, 6.2 times 10 to the negative 10. So we'll plug in that number. From our ice chart, you know that hydronium is X at equilibrium, and cyanide is also X at equilibrium. And remember, K is for your equilibrium concentrations only. So what you're doing is you're taking this entire E row, your equilibrium row, in terms of X, and you're substituting in all of those values into your Ka expression. So Ka equals x times x over 3 minus x. Plug in the given Ka value and simplify the right-hand side. Now solve for x. But this 3 minus x piece here, you might recall that our Ka value is really small. So that means not a whole lot of product is being produced. So even though we're subtracting x from that reactant side, essentially x is so small that it's really not going to change the concentration of our initial acid. So we are allowed to ignore that minus x piece because x is so small. Essentially, our weak acid molarity is not changing from initial to its equilibrium value. So if we're allowed to ignore that minus x, the math actually becomes pretty darn easy. And x ends up being 4.31 times 10 to the negative 5 molar. Now, keep in mind what x was in your ice chart. X is the molarity of hydronium at equilibrium. And that's the concentration that we plug into our pH formula. pH will be the negative log of 4.31 times 10 to the negative 5. And our final answer is 4.37, remembering that our K value only had 2 sig figs in it. Our molarity only had 2 sig figs in it, so our pH should only have 2 decimal places. Remember, pH is funny like that in terms of significant digits start after the decimal point. Now, one last part, if I wanted to calculate the percent ionization of this acid, percent ionization is equal to the equilibrium concentration of hydronium over your initial acid concentration multiplied by 100. So for this acid, the percent ionization is less than 1%. 0.0014% of the acid is ionizing and producing hydronium ions. That's extremely small percentage. This makes this an extremely weak acid because the majority of the acid molecules are not ionizing, not producing hydrogen ions. And only a very small percentage of them, 0.0014%, are ionizing. So that's a very small percentage of very weak acid. And now, one last thing to point out. Remember that we were allowed to ignore that minus x for this acid because I told you x was going to be so small because really not much of the acid is ionizing, as we can tell now with that like percent of less than 1. This is ignoring minus x piece is really called the 5% rule. you're allowed to ignore minus X when percent ionization is less than 5%. Now, you might be asking yourself, well, how do I know that it's going to be less than 5% if I haven't even calculated the percent yet? There's a real quick way to determine if it's going to be that 5% rule, and basically you're going to ignore minus X, and it is, so essentially if the initial acid concentration is 100 times greater than the Ka value, then the 5% rule is in play and you're allowed to ignore that minus X. So in our case, our Ka value is times 10 to the negative 10. And if you multiply that by 100, that is definitely still smaller than our initial concentration of 3 molar. So it is going to be 5% or less. And then we're allowed to ignore that minus X. In our class, on the AP exam, you are always allowed to ignore the minus X. It's just that we have to state on our paper that we know that we're allowed to ignore that minus X. We have to recognize or show that we understand that that minus X is really there, but we're allowed to ignore it and say that it's negligible because of the 5% rule. As long as you state that on your paper, you'll receive full credit and proceed with crossing out the minus X and simplifying your math. But in this class, yes, for any weak acid and any weak base for that matter, you'll be allowed to ignore that minus X.